Hi, thank you all for coming to my talk. I'm the first author Guangwen Chen. The work I am going to present is predicting optimal moment to deliver notifications in virtual reality. This work is conducted from National Yangming Jiao Tong University with two professors, Yongru Zhang and Liwei Chen. With the development and the popularization of virtual reality applications, users may spend more and more time in virtual reality, which will increase the need to deliver or present notifications in VR. However, previous studies have found that ear timing interruption not only impact the current activity, but also lead to a negative feeling, and for VR, an ear timing interruption may also reduce the immersion. Therefore, our research wants to predict a suitable timing to deliver notifications in VR, which could help to reduce the negative effect of the interruptions. Many previous work found that we can use contextual information to predict interruptibility. Considering the sensor feature on the VR devices is the easiest information to get, our method is mainly to use features obtained by the sensor on the commercial VR devices to predict the appropriate timing for delivering notifications. Besides the sensor data, we think that additional contextual information can be provided through VR platforms or crowdsourcing in the future. Therefore, we also try to add in information about the user's current activity and level of engagement to predict the optimal moment. There have been some studies exploring different presentations of notification in VR. But these studies are mainly to explore the design of notification display, and our research is aimed to predict a suitable timing to deliver the notification. There are also many work to investigate the prediction of interruptibility. However, previous research on predicting interruptibility has mostly focused on desktop or mobile settings rather than virtual reality. To the best of our knowledge, we are the first work to investigate the automatic prediction of the optimal moment for sending notification in VR, which is also our main contribution. To build an optimal moment prediction model, we conduct a data collection study. In order to collect diverse data in VR, we focus on two dimensions that is related to interruptibility, including the level of body movement and the need of visual attention. We use these two dimensions to design three activities, including 360 video, VR fitness, and race and game. And these three activities are also common activities in today's VR platform, such as SteamVR or Oculus. And in each activity, we deliver 4 notifications to create a realistic stimulus. User can use VR controller to respond it is a good time or bad time to receive such a notification. And the response will be a reference for user to annotate the optimal moment after the session. After each session, participants will take off their VR headset and use our annotation program to label the optimal moment and engagement level during the session. The annotation will be assisted by the first-person view video replay and their response to notifications. We recruit 20 participants with the age from 20 to 28. We use sliding window approach to sample data from continuous label data, and we ignore data which is labeled as unknown or too close to the transition boundary. We eventually produce a dataset containing about 33,000 samples, with about 40% of positive samples and the other 60% of negative samples. For the feature we use, the sensor data is mainly about the user movement index, such as the velocity of their headset or controller, as well as the change of their gaze from eye tracker. The activity information is about what is the current activity category and state, such as it is an ending screen of a recent game, or is a high-resolution 360 video. The last feature we use is a summarized engagement, which is the majority vote of all participants. For example, if 16 participants label a certain moment as high engagement, while the other 4 participants label as low engagement, we treat the moment as high engagement. For a prediction model, we use a time series neural network-based approach, which uses time series neural network to process the time series sensor data and output a feature vector, and we use fully connected layer to embed the categorical activity and engagement data into another feature vector. Then we combine these two feature vectors to make the final prediction. For the time series neural network, we explore the commonly used one-dimensional convolutional neural network, long short-term memory, and the recent work which combine the both. And we will present the best result among of these three in the following sessions. When using sensor-only feature, where the sensors are from commercial VR devices, the general model can achieve about 67% accuracy and the 0.73 AUC, or area under the RC curve, which measure the classifier's overall performance of various threshold settings, and the personalized model can achieve about 77% accuracy and the 0.88 AUC. We also found that using more sensors result in better performance for both general and personalized model. Because different sensors capture the different aspect of user movement, we further want to investigate the feature importance of each sensor for different activities, and we can find out that different sensors are important for different activities. For example, controller is least important for 360 video, and the eye tracker do not help the prediction in VR fitness. We found out that the accuracy can improve about 8% if we include activity and engagement information. Again, the personalized model also outperforms general model and can yield 85% accuracy and 0.93 AUC if we use all the sensor, activity, and engagement features. In our result, we found that personalized model outperforms general model, which indicate the individual difference of movement pattern and the perception of interoperability may not be easy to generalize to new users. However, collecting large amount of personal data could be a time-consuming task, so we suggest future work could investigate using some techniques such as user cluster or active learning to reduce the amount of personal data needed. We also found that using sensor from off-the-shelf VR device could achieve 77% accuracy and 0.88 AUC, which is comparable to previous interoperability prediction work on mobile and desktop, and the results show that each sensor is important in different activities. So we suggest future VR devices could try to provide more sensors to capture more aspects of user movement, which can be helpful to deliver notifications at better timing for different VR activities. Finally, we found that including the additional activity and summarized engagement information could further improve the model performance. Unfortunately, we cannot obtain such information for the current VR devices. So we also suggest future VR developer or platform could try to provide this information, which can help to reduce the negative impact of ear-timing interruptions. In conclusion, in our research, we investigate the feasibility to predict optimal moment to deliver notifications in virtual reality. We found out that using sensors from commercial VR devices could achieve acceptable accuracy. And by including personal data, more sensors, and additional information such as activity state or summarized engagement, we can further improve the prediction. This is the end of my talk, and thank you all for your attention.